Now, just a quick recap, and I think we were doing questions. Okay, and we were supposed to do some more questions about Le Chatelier principle. There were just three rules for Le Chatelier principle. If you increase temperature, endothermic reaction is favored. Decrease temperature, the exothermic reaction is favored. And similarly, there was another rule which was that if you increase pressure, okay, I don't know why this is missing. So the other rule was we did, I think. Let me write it over here. We had done all of this. Okay, the board wasn't working last time, so this is missing. I'm just going to quickly write down the rules that we did. What we did was that if you increase pressure, so if you increase pressure, less gas mole side is going to be it's going to be favored, and vice versa. And the last one was that if you change concentration, the equilibrium is going to try and do the opposite. If you increase concentration, the equilibrium would try to decrease concentration, and so on. And we're going to discuss what effect would change in pressure have. So we have this equilibrium going on. If I increase pressure, what does that mean? Whenever I'm going to increase, whenever we increase pressure, what's going to happen is, okay, increasing pressure, you decrease volume, you compress the thing. So whenever you increase pressure, you decrease the volume of the container. So how do I increase pressure? The way I'm going to increase pressure is I'm going to push this downwards. So when I push this downwards, the other particles, they're going to get compressed. I mean, they're going to be closer together, and there's less room for gas now. So less gas would be formed because there is no room for gas. In fact, even the molecules that have formed, they would actually condense because there is no room for gas formation. So increasing pressure decreases volume and less space available for gas. So automatically less gas would be formed. There wouldn't be a lot of water vapors forming because there's hardly any room for water vapors. And if I keep on compressing the gas or compressing the container, the volume that's available to these particles, to the vapor, it's going to be lesser and lesser. So I'm increasing pressure now. And eventually, if I increase pressure to a very large extent, even these molecules, they would be forced to change into liquid state because there would absolutely be no space available for them. So that's what happens. If you increase pressure, less gas would be formed. There's no room for gas formation. Vice versa, if I decrease pressure. So the other one is if I decrease pressure, that means I'm increasing volume. I'm decompressing. I increase volume, and when I increase volume, so I'm going to try and increase the volume. That means I'm going to push the piston outwards. So if I'm moving the piston outwards, I'm decreasing pressure. So this is what we're doing now. Now there's more room for vapor to form. So more evaporation would happen and more gas is going to be formed because there's a lot of space available now for the gas to be formed. So there's going to be more evaporation. So if you decrease pressure, you increase volume and more gas is formed. So it's a simple rule, and I'm applying this rule to this equilibrium, this liquid water and gaseous water vapors are in equilibrium. So increasing pressure, you're compressing it, less gas is formed. If you're decreasing pressure, you're decompressing it, then more gas is formed. So that's the main rule. Is this rule clear to everyone? Yes or no? Is this clear? And what we can state is what we can state here is that less gas is formed. What we can state is that less gas mole side is favored. The side that produces less gas, and the other side is more gas mole side is favored. So the equilibrium is going to have two sides, the forward and the backward. So for example, if you have a reaction that's going on and the reaction is N2 plus 3H2 in equilibrium with 2NH3. So it's a separate question and all of them are gases. So if I have this reaction going on and I'm being asked to tell what's going to happen if I increase pressure, then automatically it's understood that if you're increasing pressure, you're decreasing volume and less gas would be formed. So the side that produces less gas moles, that is the side that should be favored, which in this case, I mean, you're going to count the number of moles. If you count the number of moles over here, so these are your two sides. If the reaction moves in the forward direction, 2 moles of gas are produced. If the reaction moves in the backward direction, then 4 moles of gas are produced. So if the reaction happens to move in the backward direction, you get 4 molecules of gas. If the reaction moves in the forward direction, you get 2 molecules of gas. So less gas mole side is favored. So that means the forward reaction is going to be favored in this case. So forward reaction is favored and equilibrium shifts to the right side. So equilibrium shifts to right hand side. ठीक है, is this part clear? So next is and we can do a few more examples. Uh, let's say there's another question. And this other question is you have, let's say you have H2CO3, which is your carbon. This is in carbonated drinks. You have carbonic acid, which is when water absorbs carbon dioxide, it forms carbonic acid. So this is aqueous, this is liquid, and this is carbon dioxide gas. What happens when you release pressure? For example, if you open a can, you're releasing pressure, you're decreasing pressure. So when you decrease pressure, more gas mole side is favored. So more gas mole side is going to be favored, and on the right side you have 1 molecule of gas. So 1 mole of gas is being formed if the reaction moves in the forward direction, and if it moves in the backward direction, there is no gas. So 0 moles of gas. You can only count the moles of gas. So more gas is going to be produced if the reaction moves in the forward direction. So more gas mole side is favored, and basically forward reaction would be favored. I mean, because there is no gas. I mean, H2CO3 moles of gas. How many? If it moves in the backward direction, you can think of it moving in the backward direction. How many moles of gas would be produced? I mean, there is no gas. So which is why zero. You're only going to count the moles of gas. Sanjida, is this clear? So I mean, that's why I gave you this example. You're not going to count. We're only going to look at the moles of gas. Less gas, more gas. And also remember these 2 points. And the points are that number one, the point that you must remember is there's going to be no effect on equilibrium position if there is no gas altogether in a reaction. So no effect in equilibrium position because pressure, only gases are compressible. Liquids and solids are not compressible. Pressure is not going to have any effect on a liquid or a solid. I mean, they're not compressible, or they're not, or they're very, very slightly compressible. So pressure is not going to have any effect, no effect on equilibrium position if there happen to be two scenarios. There are no moles of gas in the equilibrium, or if both sides have equal moles of gas. Now that is also one of the scenarios. So if both sides have equal moles of gas, one example could be that if you have H2 gas reacting with Cl2 gas and they're in equilibrium with HCl gas. All of them are gases, and both sides, if the reaction moves forward, it produces 2 moles of gas. If the reaction moves backwards, it still produces 2 moles of gas. So in this case, the equilibrium is not going to shift, because if you're compressing, uh, it doesn't really matter. It's going to remain wherever it is, because shifting sides would have no effect on the pressure. So next one, the last one. Okay, hopefully this part is clear. Uh, the next part is, the last one is changing concentration. So the last point is, and the last equilibrium, the Chatelier principle rule is, rule number 3 is, if you increase concentration of anything, reactant or product, okay, so reactant or product, anything, then equilibrium would try to do the opposite. Would try to do the opposite, and it would try to decrease concentration and favors that reaction that decreases concentration. And vice versa. So if I try to, let's take that example again, the water example. Exactly. So we're going to take the example of water again. You have liquid water. H2O is in liquid state. And it's evaporating and it's forming these gaseous vapors, and they are in equilibrium. They're going forward, and the reaction is going backward. Both evaporation and condensation are happening. So if I try to decrease something in this equilibrium, let's say, for example, I open the container and I remove water vapors. And that's what I'm doing. I'm introducing this change. I'm removing all the water vapors. I've opened the container and removed all the water vapors. What would the equilibrium do? I mean, previously there was a forward and backward reaction happening. Evaporation was happening and condensation was happening as well. Now I've removed, all of a sudden I went inside and I've removed all the water vapors. So automatically, this reaction, one of the reaction, the condensation would stop. Why would it stop? Because there is no water vapor to condense. But the evaporation would still continue. So more water vapors would be formed eventually. And when water vapors form, they're going to start the condensation reaction back again. But the main point is, if I try to remove water vapors, then obviously more evaporation would happen and more water vapors would be formed. So it's Very simple. So no matter what you do, it's going to do the opposite. If you try to increase water vapors, let's say you open the container and you add a lot of water vapors into this, then obviously condensation would speed up. Why? Because you have so many water vapors that condensation would automatically speed up, and more molecules, because there's so many water vapors. So if I try to increase water vapors, the equilibrium would automatically shift and favor that reaction that decreases water vapors. So it's going to try and do the opposite. Get rid of water vapors, it's going to eventually make more water vapors. More evaporation would happen and water vapors would reform. So it just does the opposite. Okay? So it's going to favor that reaction. So I'm going to apply that rule to any equilibrium mixture. For example, I have this reaction SO2 plus O2, and it's in equilibrium with 2SO3, and they're all gases. So let's say I go in and I decrease the concentration of O2. What would the equilibrium do? Equilibrium is going to do the opposite. Equilibrium is going to try and equilibrium tries to make more oxygen. It's going to try and make more oxygen. So if I try to decrease O2, then it's going to favor the backward reaction. It's going to try and make more oxygen. So backward reaction would be favored. Is this point clear? Yes or no? Is this clear, Rida? Sanjita, is this clear? So these are your 3 points, and we're going to start, and I'm going to sum them up. The main 3 points are uh, increased temperature, endothermic would be favored. And remember, this is not. I told you that when we talk about the Le-Chatelier principle, we're not talking about the speed of the reaction. We're just talking about the relative comparison. Which one is faster relatively compared to the other one? Decreased temperature, it's the exothermic reaction that's going to be favored. If you increase pressure, then less gas moles side is favored, or less gas would be formed. If you decrease pressure, it's going to do the opposite. More gas is formed. And lastly, if you increase concentration of anything, it's going to try and decrease concentration. And vice versa, if you try to decrease concentration, it's going to try and favor that reaction that increases concentration. And remember, the reaction would use the word favored, not speed. So these are your rules, and we're going to look at the questions now of Le-Chatelier principle. This is a worksheet on Le-Chatelier principle, and we're going to start with the first one. As the questions are not going to be very straightforward, there might be just 1 second. Let's forget this. Maybe this one. Just 1 second. So we can actually start with the simple questions first. This one. 1 second. Let me. I shall go back to the board. Sanjita, this is the board. What you can try and do is you can try and I'll send you the link to the board as well, so you can open it at your end as well. Okay, but you can have this board open at your end. So now coming back to the questions, we can do the simple questions first. Now, for which so you're given this reaction and you're being asked which what caused the position of the equilibrium to shift to the right. So he wants the equilibrium position to move to the right side, forward reaction. So we're going to have a look at this, and one by one we're going to discuss. The first one, if you decrease concentration of H2S, equilibrium is going to try and do the opposite. It's going to try and increase H2S. So how can it increase H2S? It's going to favor the backward reaction. So that is definitely not the answer. In this case, it's going to be the backward. So we're looking for the forward reaction. So let's simply erase that. The next one is increase the pressure on the system. If I increase the pressure on the system, it's going to favor the less increasing pressure. It's going to favor less gas moles. So less gas mole side is favored, which in this case would be which side? Over here I have a total of 5 moles of gas. On the left side I have 1 molecule of CH4, 2 molecules of H2S. So that's 3 moles. So which side is the less gas mole side? It's going to be the backward reaction again. So again, not the correct answer. The next one is he's asking us to increase or decrease the temperature of the system. Now for that we need to we need to know which one is endothermic, which one is exothermic, which we actually it's not given in the question. So I think you're not sure. So we can actually ignore this for now. TK, maybe this is just a random worksheet from the internet, so we can ignore this because we don't know what endothermic, which one is endo, which one is exo at the moment. Increase concentration of carbon disulfide, so it's going to try and do the opposite. It's going to try and decrease carbon disulfide, CH2. So the only way CH2 could be decreased is that if the backward reaction is favored. So again, it's going to be the backward reaction. And the next one is decrease the concentration of methane. So if I decrease the concentration of methane, it's going to try and make more methane. It's going to try and increase methane. And the only way that's possible is, again, if backward is favored. It can't be E because the thing is the answer is actually C, but we're not given enough data to get C. So Gita, is this clear that all of these are wrong? I mean, they're all favoring backward. TK, the one that we actually did not do, that must probably be the right answer. Is this clear? I mean, there's something wrong. The only thing wrong with this question is that we don't know which one is endo, which one is exo, so we can't really solve for C. But otherwise, the rest of the options are they clear? Why these 4 are wrong? Achha, so similarly, next one. Now he's saying what would happen to the position of the equilibrium when the following changes are made. So we need to figure out whether forward or backward. So sulfur dioxide is added. So that means SO2 concentration. Remember, concentrations are written in square brackets. SO2 increases. What would the equilibrium do? Equilibrium would try to decrease. It would tries to decrease SO2. So how can SO2 be decreased? By favoring the backward reaction, because the forward is going to produce even more SO2. We want lesser SO2, so convert the SO2 into SO3. So in this case, the first one, it's going to be backward. The next one is sulfur trioxide is removed from the system. If it's removed from the system, the equilibrium is going to try and do the opposite. It's going to try and increase SO3 concentration. That's what the equilibrium would try and do. It's going to do the opposite. How can SO3 be increased? Again, backward. It's going to try and make more SO3. The next one is oxygen is added to the system. So if you add oxygen to the system, it's going to try and remove oxygen from the system or decrease O2. How can O2 be decreased if the backward reaction is favored? Only then can O2 be removed. Okay, so I think all of them, all three were actually backward in this case. Okay, is this clear? So we can now switch towards these AS questions. Okay, they would be slightly more tricky. So, for example, this question, the first one that you see over here, uh, the first reaction is the equilibrium reaction. I mean, this is the equilibrium reaction. So let's read the question carefully. They're saying that swimming pool water can be kept free of harmful bacteria by adding aqueous sodium chloride. This reacts with water to produce HOCl molecules which kill bacteria. So there's this reaction happening and it's in equilibrium. In bright sunshine, the OCl ions are broken down by ultraviolet light. So if the sunlight is very bright, then the OCl ions over here that you see over here, they get broken down. And this is not reversible. Remember, this is not a reversible reaction. Once this reaction happens, it's a one-sided reaction. Now, which method would maintain the highest concentration of HOCl? Now, HOCl is present in the first reaction. This is where HOCl is. What do we need to do? We need to sort of shift the equilibrium in the forward direction. We want more forward reaction. The more forward the reaction, the more HOCl that's going to be produced in this case. So we need more HOCl. I mean, that's what the whole question is. We need to maintain the highest concentration of HOCl. Now, the first one, acidify the pool. So, what does that mean, acidify the pool? Acidify the pool means that you add H plus 1 ions. I mean, that's what an acid does. You get H plus 1 ions in the solution. Now, the thing is that if something is at equilibrium, I mean, like this one, if it's at equilibrium, then if there is something you're adding that's not even present in the equilibrium is going to remain unaffected. Like, for example, over here, in the questions that we did, if I if I had added NO2 gas over here, this equilibrium would be unaffected. So if you're adding a random substance to the mixture, the equilibrium would remain completely unaffected. Nothing would happen to it. Uh, so something must happen to these three things. Only then would the position of the equilibrium be changed. So if we go back, you're adding H plus 1 ions. Now the thing with H plus 1 ions is that H plus 1 ions are going to affect this equilibrium over here. The way they're going to affect the equilibrium is that H plus 1 ions tend to neutralize OH ions and they end up producing water molecules. So that means if you add H plus 1 ions, the quantity of OH ions would decrease. I mean, the OH ions would be neutralized. So the equilibrium is going to be affected. By adding or acidifying the pool water, there's going to be less OH ions in the solution. So if OH ions decrease, what you're doing is you're decreasing OH ions. Then what would the equilibrium do? Equilibrium would try to do the opposite. Equilibrium would try to make more OH ions. it's going to try and make more OH ions. And the only way it can make more OH ions is by favoring the forward reaction. And if the forward reaction is favored, then automatically there's going to be more HOCl formed as well. So I'm going to repeat. You add acid, the acid would go and neutralize the OH ions. If the OH ions are neutralized and the quantity decreases, the equilibrium would try to do the opposite and it would try to make more OH ions. Hence, the forward reaction would be favored, and you get more HOCl. So option A is definitely correct. Did everyone get this? Sanjida, Rida, is this clear? I'll come to that. Okay, but hopefully the first part. So let's look at the other ions. Let's look at the other options. So adding Cl ions. So if I try to add Cl ions, let's get rid of this now. So this part is done. So, so I'm just quickly go through them, go through all the options. I said if you add Cl lines, the Cl lines, the only place Cl lines are present in this are this place over here. But this is not a reversible reaction, so nothing would happen because it is a product and it's not going to go back, so nothing would happen over here. And if you add a solution of hydroxide ions, so the concentration of OH ions would increase. The equilibrium would try to decrease OH ions, so it's going to favor the backward reaction. And in that way, even HOCl would decrease. And bubble air through water, air contains oxygen gas. So bubbling air through water would probably not affect anything because it's again not an equilibrium reaction. So let's move to the next part. The question now is sulfur dioxide and oxygen react in the gas phase. So, so they react in the gas phase. Which statement are correct? Increasing pressure increases the yield. Yield means output. Whenever they talk about yield, that means output or product. So do you get more product or do you get less product? So increasing pressure. If you increase pressure, which side is favored? The less gas moles side. So less gas moles side. Over here you have 2 moles of gas. On the backward side you have 3 moles of gas. You have 2 moles of SO2 and 1 mole of O2. So if you increase pressure, less gas moles. So that means forward reaction would be favored. Is this clear? Usman, is this clear? Reda, is this clear? So the first option is correct. It is correct. I mean, you're going to get more products. The second one is increasing temperature lowers the value of the equilibrium constant Kp. So we haven't done Kp right now. Let's ignore Kp. Let's not answer the question, but let's just figure out what's going to happen if you increase temperature. Increasing temperature favors which reaction? It's going to favor, number two, it's going to favor the endothermic reaction. So how do you figure out which one is the endothermic reaction? Uh, Remember, the enthalpy change is always given for the forward reaction, which is with a minus sign. So that means the forward is the one that's exo actually. So the forward reaction is exo. The backward is going to be the opposite. It's going to be endo. The backward would be endo. So you have an exothermic reaction and you have an endothermic reaction. So endothermic reaction would be favored if you increase temperature, which in this case would be the backward reaction. So it's going to be the backward reaction. So, I mean, we haven't studied Kp, so we're not going to answer that part. What does the catalyst do? And remember, we haven't discussed catalyst. Remember what a catalyst would do. Catalyst has no effect on the equilibrium position. Why it has no effect? Because it's going to favor both the forward and the backward reactions equally. It reduces activation energy. and it speeds up both the forward and the backward reactions equally. So it speeds up both the forward and the backward reactions equally. That is what a catalyst would do. Okay, so catalyst, remember, has absolutely no effect on the equilibrium position. Okay, is this question clear? So then the next part is once. So the next part is which statement about reversible reactions is correct? An increase in concentration of a reactant always increases the concentration. The first statement. So increasing the concentration of a reactant. So you have an equilibrium that's going on, reactants in equilibrium with products. So if I try to increase the concentration of a reactant, the equilibrium is going to try and do the opposite. Equilibrium would try to decrease the reactant, which means it's going to favor the forward reaction. So as a result, the product would increase. So the first statement is correct that if you try to increase the concentration of a reactant, the concentration of the product would obviously increase because the equilibrium would try to do the opposite. It's going to reduce the quantity of the reactant and change it into products. So the amount of products would actually increase. So that is always true. The second statement, increase in temperature always increases the rate at which the equilibrium is established. Now this is, I told you, be very careful when they're talking about rate of reaction. Rate has nothing to do with equilibrium. You can remember when we talk about forward and backward, I'm stressing it over and over again. It has nothing to do with the speed of the reaction. It just means that one of the reaction is faster compared to the other one. Maybe both reactions are slowing down, maybe both reactions are speeding up. So treat rate as something that is separate. So whenever you increase temperature, the rate of the reaction always increases. So this statement is correct that whenever you increase temperature, there's going to be an increase in the rate. The speed of the reaction is going to be higher, whether it's the backward or the forward, no matter which reaction it is. The speed of the reaction would be higher. Next one is an increase in temperature always increases the concentration of the products. I mean, this statement is incorrect because if you increase the temperature, which reaction is favored? It's the endothermic reaction that's favored. Now, you don't know whether the endothermic is the one that's making the products or whether the exothermic is the one that's making the products because endo and exo varies from reaction to reaction. So this statement cannot always be correct. Whenever you increase temperature, this is always correct that always endothermic reaction is favored. But the endothermic could be the backward reaction, it could be the forward reaction. It depends on the reaction and it varies from reaction to reaction. So hence, it's not always that the product are going to be formed. Okay, is this clear? I said then the next part. Let's do one more question. I said let's talk about this question. When vanadium compounds are dissolved in water, the following equilibrium is established. What would alter the position of the equilibrium mixture in favor of V2 plus ions? As again, you have, as a in favor of V2 plus ions, you want more V2 plus ions. You want the backward reaction to happen. More V2 plus ions. That's what the question is. That the mixture should contain or should favor V2 plus ions. More V2 plus ions, the backward. So one by one, starting with the first point. Now the first point is you add an acid, H plus O ions. And I told you previously that H plus ones, they neutralize the OH ions to form water. So immediately, let's ignore this. So immediately what would happen? The OH ions would be removed if you add H plus 1 ions. If you add too many H plus 1 ions, the OH ions are going to get neutralized. So if you're neutralizing the OH ions, if you're decreasing the quantity of OH ions, the equilibrium is going to try and make more OH ions. So we don't want the reaction to go in that direction. So the first one is it's definitely incorrect. The next one is adding a reagent that selectively precipitates P3 plus ions. What does precipitate mean? Precipitate means that you're adding something. I mean, like if a solution contains silver ions and you add Cl ions to it, immediately they're going to get together to form an insoluble precipitate of AgCl solid. So the silver ions and the Cl ions would be removed from the solution. So adding a reagent that selectively precipitates V3 plus ions means that you're removing V3 plus ions from the solution. You're adding something which is going to combine with the V3 plus ions and they're going to form a solid. Like, I mean, we don't know what V3 plus ions, we haven't studied the solubility of V3 plus ions. So we have no idea, but you're adding something that's going to make it insoluble. So the solution is going to have less V3 plus ions because all of them would have formed a precipitate and they would have been removed from the solution. So if V3 plus ions are gone and they're lesser, the equilibrium would try to make more of them. So again, backward reaction is going to be favored. Option C, so this is also incorrect. We don't want the reaction to go in the forward direction. Allowing the hydrogen to escape, if you allow the hydrogen to escape, so that means there's less H2. You've allowed the hydrogen to escape. The equilibrium would try to make more H2. So again, backward. So we don't want that to happen, making the solution more alkaline. So if you increase OH ions, the equilibrium would try to decrease OH ions. That's the right one. It's going to convert the OH ions back into, so V2 plus ions would be formed. So option D would be the correct option in this case. Is this question clear? Ridab, Sanjita, is this clear? Okay, we're going to continue with this tomorrow then. And we're going to move to something else. I'll send this as a worksheet, post this on the classroom. Okay. Okay, then take care. Allah Hafiz.